Hi everyone, welcome again. Now our second speaker, Lin Chen from Carnegie Mellon University. She will talk about an optimal mass transport method for random genetic drift problem. Lin, you can start.
Oh, okay. Can I share my screen? Okay.
Yes.
Okay. Thank you for the introduction of Virginia. And today my topic is an optimal mass transport method for random genetic drift problem. This work, I did this work 2 years ago, and is a joint work with Professor Creer from Oxford and Professor Wang from Southwestern University in Finance and Economics. And this paper was published on some journal on numeric analysis this year. And I'm second-year PhD students of Math Department of CMU. And let's start. Oh, wait a second. Okay. I think first I will introduce the random genetic drift problem. As we can see that in the population genetic drift, the genetic drift describes the random fluctuation in the numbers of allele. Here, allele means the variant of each gene. As we can see in this picture, each individual have different combination of gene, so that's why we are different. And look at an example here. This represents a gene pool. Assume that we have each individual here is distinguished by their two neutral alleles labeled by A and B, and this is red ball and also a blue ball. We can use these balls to represent alleles inside this gene pool. And so we can get the first generation. Assume that the allele frequency for the dominant one, here we means the red one is P, and the allele frequency for the blue one is the Q. And in this case, we can show that if we randomly choose one ball here to reproduce offspring, and then we can choose another one to be replaced. It means B here, and then we can see that in the second generation, the allele frequency of the red one increase a little bit. For this process, we can do it again and again after each time steps, and then we can find that the blue one dominates. It means that the frequency of the blue one fixed, and however, the red one disappear. From this example, we can see that genetic drift can decrease the popular genetic diversity, and it plays an important role in the evolution of the new species. And then we can see a simulation here. Now, wait a second. I think, oh, wait. I think I cannot. Something wrong here. I cannot prove it.
Is it like a video?
Yeah, it's a video, but I cannot wait. I think I can, but maybe we can see the original picture. Oh, sorry, I cannot play this one, but it doesn't matter.
It's fine. You can.
Yeah, it's fine. Yeah. The thing we can show that if we set a random allele frequency for the A and the B, here I set actually A to be 0.4 here, and I can set the B frequency to be 0.6 here, and eventually we can see the B frequency will go to 0, and while the A frequency can go to 1. And this can show the random genetic process. Okay, let's both go back to math now. In the 1920s, Wright and Fisher proposed some discrete stochastic models to describe this process. And later on, Kimmer and Morrow also extend this model, and they prove that in the limit of large population and weak selection, this process can be formed as a Kimmer equation. And that's the model I will discuss later. As we can see in this formula, there exists some singularity on the boundary x equals 0 and x is equal to 1. It means that, and we can always expect that the solution will blow up on the boundary if we do some numeric simulation. And here is some theoretical result about this equation. As we can see that if we give the initial data to be the positive random measure function, and we can show this function admit a unique weak solution f belongs to this set, and it satisfies the conservation law. And also we can see the solution can be expressed of the combination of a classical solution and some boundary spike here. And this AT and BT depends on the initial data. According to these theoretical results, we can see that the theoretic solution will blow up into the delta boundary spike later. And here is the result here. And so that puts some numeric results, numeric difficulty. You cannot use some numeric scheme to show that some solution blow up. So we want to find another way to achieve this solution numerically. As we can see, there is some results about the optimal transport posed by these mathematicians in 2019. They proved that the solution of the Kimmer equation can be regarded as the gradient flow with respect to a resistance distance. This is not a standard resistance distance. And they prove that for the pure distribution case, they have the numerical results. And I will skip the optimal transport theory here. There are just some basic concept here. And we want to use their gradient flow structure to construct another scheme to prove that for the general Kimmer solution, we can simulation the behaviors of the F. And our idea is that we don't simulate the original function F. We want to transform it into another function, which means the pseudo-inverse function. It can be expressed as the inverse of the distribution function. According to the optimal transport theory, we know that in the one-dimension case, we can write the optimal. We can explicitly express the optimal plan here, and then we get the express formula for the resistance distance. Because for the definition here, we need to take the informal over some transport plan here. But for the higher dimension, we cannot get the explicit expression. We can only get it in the one-dimension case. So we can rewrite the resistance distance as this formula. Here, mu and nu are some positive measure. So we can, since we want to solve a solution, some density function solution, we can regard it as the probability measure. And then we denote this one as the inverse function, inverse cumulative distribution as the new variable. According to the definition here, we can transform our F. Here, F is the cumulative distribution of little f, and then we can transform our formula Kimmer equation into another form, we can express it as a new function phi here. And we get a well-main result. It means that we can use a map phi here to push forward the initial data f into the solution f, and the convergence of the original function f is equals to the convergence of the new function phi, and we only need to do is to prove the convergence of phi instead of the convergence f. And phi has some very good probability with respect to the f. You can see that the steady state for phi is the step function with value 0 and y, whereas as we discussed before, for the function f, it will blow up into a delta function. But phi is a step function, which means that we can solve it numerically. And let's discuss about our scheme here. In terms of the resistance distance, we want to use the J-code steep descent scheme to find the solution. And is equivalent to solve the following minimization problem. It means that the phi k plus 1 can be achieved as the minimizer of this new functional. Here, what we need to do is to take the first variation of this new functional, and the phi k plus 1 is the minimizer of this functional. And use the definition of phi before, because we defined phi to be the inverse function of the cumulative distribution function. So we can, since we have the formula for f, we also have the formula for the energy of phi. It can be given as this formula. And use the expression of the resistance distance and also the tunnel expansion, we can get the first variation of the resistance distance is approximated by this formula. Since we want to take the first variation of the whole functional, and then we want to this first variation of this functional equals to 0, then we can get our implicit Euler scheme. If we denote the numeric solution as this formula for giving the measure size k and the time size tau, then we get our implicit Euler scheme as follows. You can see we have something like the refraction here because we get the variation of the resistance distance can be expressed as this one. And also, if phi goes to 0 or phi goes to 1, we have the singularity of this scheme. So let's see our problems as before. Here we know that this functional is a non-convex functional. So it means that we cannot solve the implicit Euler scheme directly because we don't have the convergence of the Newton method. So we propose proper sensing step for our scheme. It's called convex splitting technology. As we know that for each functional, we can express it as the difference of two convex functions. So if we write the function v as the difference of two convex functions, we can also express our energy to be the difference of two convex functions as follows. And then the convex splitting method means that you can put the implicit method for the convex part and put the explicit formula for the non-convex part. So we can get another semi-discrete scheme here. It's different from our mainly Euler implicit scheme before, but we want to solve it as our pre-step. In particular, we can see that the map from our phi k to the phi k plus 1 is optimal transport in sense of that the phi k plus 1 minimize a new functional here. And here W is the convex functional. We can express it as this one. And first, and then we can, if we write the nonlinear functional as this way, it's just the difference between this formula from the difference with the difference between the right-hand side and the left-hand side. We just do the standard Newton update as this way, and however, the update step is not one, is defined as another parameter here. And then we want to prove the convergence of our two schemes. First one, we need to prove the solvability of our convex splitting schemes. If we define a discrete space domain as this one, this is just the discrete space, and we define the boundary as this formula. Then we can prove that our complete convex splitting scheme is unique solvable. And the proof is very easy because, as we mentioned before, we can regard our scheme as the minimizer of this functional, and this functional is a convex functional. So it's equivalent to solve the unique minimizer of this functional. So we can also get the solvable of our convex splitting scheme. And then we also want to prove the convergence of the Newton method, because we use another dumped Newton method for the convex splitting method. We prove that this Newton method is convergent in the discrete space. Later on, we also prove that the convex splitting method have the dissipation of energy. If we define phi I to be a strictly increasing sequence as this way, because if phi I is non-decreasing, then there exists some singularity in the log function here. So we need to define phi to be some strictly increasing sequence as this way. And then we can write our discrete free energy as this way. And we can prove that this energy is decreasing, which means that we have the dissipation of the energy. And later on, we want to prove our main theory, our convergence of our implicit Euler scheme. First, we prove that if phi is an increasing sequence with a boundary condition, then the energy is bounded from below for any positive step size, which means that we have the existence of our steady state. And we want to show that our steady state is step function with this formula, with this form here. And so we can define some discrete formula as this one, and we can prove that our steady state can be expressed as the step function. And also we prove that if the v prime have don't change the sign, which means that v is increasing or decreasing, then we can also prove that the steady state must be the step function. Here we prove for the pure diffusion model with the v prime equals to 0, which means that v equals to constant, we can give the formula for the A and M here. A and M here, we can express explicit form. We can give the explicit formula for them. And however, if v is a general one, which means that v is not decreasing or increasing, then we can only prove that the step function is the step function is the steady state of our numeric scheme, but we cannot prove that our numeric scheme has only the step function size from has only the step function steady state. And I skip the proof here because it can be found in our paper. And I want to show some simulation later. And then we also prove some convergence of our theory. We can prove that our implicit numeric scheme is convergent, is exponentially decay for the case v prime equals to 0. And for the general case, if v prime is non-positive or non-negative, we can prove that if the step size, if the steps, we can prove that there exists some, we can prove that we have some, if the time sums goes to 0 modulo a big O h term, then we can prove the exponential decay for our numeric scheme. And now we can see some numeric simulation here. Sorry, I think I know the problem here. I want to, oh wait. Can you see my screen?
Yeah, we can see.
Oh, sorry. Yeah, I think I touched something. Wait a second. Okay, it's done now. Oh, yeah, it worked now. Sorry. Okay, let's go back to our theory here. Yeah. Okay, so let's see some numerical result here. First, we want to study our convergence of the numerical scheme. Here we investigate the diffusion equation, which means that we don't have the v prime equals to 0 in our formula. So we can express the discrete L1 norm as this formula. Here, phi ik reference means that if we choose the measure size to be small enough and the time size to be small enough, it can approximate the real value. So we want to compute the distance between our numeric solution and our reference solution here. And the order of convergence in spatial can be defined as this way. And we can also define our order of convergence in time as this way. It means that we change our h to be h1/2, and here we can decrease our time step to be from tau to be tau over 2. And there's some table shows the convergence in spatial size and also the time size here. And you can see that the conversion order is bigger than 1 if we decrease the size of space, and also for this one here, if we decrease our time step by 2, then the order of convergence is greater than 1 as the time steps decrease. And I choose 2 different initial data here. The first one is the symmetric one, and another one is the asymmetric one. But they have the similar results here. And let's see their picture here. As I mentioned before, we want to solve the Kimmer equation numerically. However, the solution for the solution will blow up as the time goes by. So we can see the picture right-hand side, it will blow up into the boundary spike as this way. So alternatively, we want to find another function that has different behaviors in numerical. And this is our new function phi here. Phi is the inverse function of the cumulative distribution function. So it will converge to the step function. The red one means the initial data. The red one here, okay. The initial data we choose as this formula here is the symmetric formula, and it will blow up into the boundary spike. And if we transform this formula F0 to be a initial function phi 0 as this way, so is the increasing function because the cumulative function is increasing 1, so the inverse function is also increasing 1, and the phi function will converge to the step function as this way. So actually, we can get the behavior of the function f by solve the formula for the phi. However, phi is bounded function, and phi has a very good probability. And here we also verify our theoretical result here. As we mentioned before, first, our solution will converge to a step function. The blue line shows that the initial diffeomorphism phi is something like this one, and it will go to the step function as this way, and also is true for this one. And we can also see the energy dissipation of phi. We only prove the energy dissipation for the convex splitting scheme. We don't prove it for the implicit method, but we have it by the numerical result. And here we show the convergence rate. The black line here is our theoretical result, and we can find that our convergence rate is very close to the theoretical result at the beginning. And here, the same way here. And finally, we checked our main result here. As we mentioned before, phi goes to some step function, and the jump point is determined by the formula here. And we want to check these results by our numerical results. So here we can check it. If we choose different v prime as this way, and we choose different initial data, we can find that the theoretical jump point is close to the numeric jump point. And that's all our results. And that's some reference inside the talk. And thank you. I think that's all. Do you have any question?
Thank you, Lin, for the talk.
Sorry.